Okay guys, I'm back with two more problems on this problem session number 5. Both of these last two problems have to do with doing some estimations, estimating some values here. So I want to practice this a little bit. We've learned Taylor's theorem, we know the mean value theorem. We're going to use those tools to help us do some approximations. Okay? In particular here, we want to give an approximation for the square root of 105. And we're going to use the mean value theorem to do it. Maybe I should have written down the mean value theorem again. It just says, again, if you have a closed interval AB and you have a continuous function, f of x, all right, then there exists a c in the open interval AB, and f prime of c is just f of b minus f of a over b minus a. So it's just a summary of the mean value theorem. We're going to use that here. In order to use it, I have to have these pieces in place, right? So, well, for one thing, I have to come up with a function. Looking at what we're trying to estimate, I think it might be reasonable, so if you want to think before you continue with the video, you can pause the video here. Think about what function should we use? What f of x should we use to estimate the square root of 105? Okay? Great. So the answer is, as you probably know, we're going to use the square root of x. Okay? And now we need to make an interval out of this problem, an interval AB. The square root of 105 is fairly close to the square root of 100. So I'm going to suggest that we use the interval from 100 to 105. Okay? Make that closed interval. Okay? So then by the mean value theorem, let me just go ahead and state what we would now have. By the mean value theorem applied to this interval and this function, right, what we can say is there exists a c in the open interval from 100 to 105 with f prime of c equals f of 105 minus f of 100 over 105 minus 100, right? That's the mean value theorem. Okay. Now, the derivative of the square root of x is just 1 over 2 square root of x, and I'm going to plug in c into that, right? F of 105 is just the number we're trying to estimate, square root of 105, and then I'm going to subtract 10 here, and I'm going to put 5 on the bottom as well. Okay, so based on that, I can actually already write down, let me go ahead and erase this part, I can already write down sort of a formula for the square root of 105, right, if I solve for it. So what would it be? The square root of 105 would equal 10 plus 5 over 2 radical c. Okay, so we have that right there. Okay, so far so good. I want to put a number in, I want to replace c with something else that we can actually evaluate so that we can get a numerical estimate for the square root of 105. Okay? Now notice that c is bigger than 100, right? So if I were to change the c and reduce it down to 100, that would make this denominator smaller, which would make this whole thing become bigger, right? So in other words, what we have here currently, what we currently have here is less than if we replace the c with 100, okay? So I've made the denominator smaller, which is making this whole thing bigger. But the nice thing now is I can put in an estimate. I can actually calculate this. This is going to be 10 plus 5 divided by 20, right? In other words, it's 10.25. Okay? So the square root of 105 has an upper bound. We were asked to give both upper and lower bounds. This would be an upper bound right here. An upper bound would be 10.25. Okay? What about getting a lower bound on this thing? Well, I also know that, okay, so clearly c is less than 105, but I don't really want to replace, so see, when I replaced the c with a 100, right, it made this part bigger, and it was easy to calculate this in our heads. You might be thinking, well, to get the inequality to go the other way, right, to get a lower bound, I would want to make this denominator bigger, and I could do that. I could say, well, the biggest that c could be is the square root of 105, because c is somewhere in here. But the thing is that I don't know what this number is, right? I'm kind of estimating radical 105 with something that has radical 105 in it. You don't want to do that, right? That's kind of going in circles with it. So what you want to do instead is say, you know, it's all right to actually increase c even more to some number that might be outside of this interval that would be easy to calculate. And so that's the trick here. So what we're going to do is we're going to replace the c with 121, because the square root of 121 is easy to calculate. So, and it's the first number that's bigger than 105 that's easy to evaluate. I mean, you might say, well, why couldn't I just replace this with, you know, 10,000 or something? You could, but then you're going to be getting a lower bound that is not as good. Okay? The problem was a little bit loose. It doesn't say how good the upper bound or the lower bound needs to be. So you wouldn't have to use 121 here. You could use 144 or 169 or, you know, as I said, any number that is bigger than 105 would be reasonable here. Okay? But this is kind of the best one that's like easy to use. Okay? So we use that, and it turns out you get, I've got this calculated. This, of course, was done with a calculator, but you get 10.2272. Okay, so at the end of the day here, 10.2272 is less than radical 105, is less than 10.25. Right, so it's somewhere between those two numbers. Right, that's your estimate that you are looking for. Okay. All right, so that's a good example. I wouldn't ask it quite like this if it was going to be on a test or something, because it is a little vague. It doesn't say how good these upper and lower bounds need to be. Okay, but you get the idea here. You take this, basically this formula right here that comes from the using the mean value theorem directly, and you just you replace this c with sort of the two nicest numbers, one above and one below that interval from 100 to 105, and that gives you the two sides of this bound that we're looking at right here. Okay? Great. So that is number 5. All right. Again, if any of these are giving you any trouble, by all means, rewind if you need to. Take it a little slower, and then come see me about them if you'd like to. Okay? One last problem I want to go over with you guys. This actually has 3 parts to it. So might take us a minute to go through this. So number 6 here, it says show that for all x greater than or equal to 0, 1 plus 1/2 x minus 1/8 of x squared is less than or equal to the square root of 1 plus x. Okay? So again, you might want to pause if you want to think about this a little bit, what things that we've learned recently are going to be useful for this. Okay? What you might have noticed is that the left side looks like a polynomial, okay, of degree 2. The right-hand side gives us a clue into possibly creating a function. And when we're thinking about using polynomial approximations to functions, we're thinking about Taylor's theorem. So if that's what you were thinking, good for you. That's exactly the right idea. Now, to use Taylor's theorem, to work on Taylor's theorem, we need to have a closed interval. At the moment, they don't really give us a closed interval. However, notice that we have x and we have 0. Okay. Now, the way it's stated, x could equal 0. But the thing is, if x is equal to 0, you can just literally plug in. You can literally plug in 0 for x and just verify that this is already true. Okay. So it's already true. So we may assume that x is actually positive, and then we can form, therefore, a closed interval from 0 to x. That's kind of the idea. That's kind of the idea here. So we have this closed interval like that. that we can kind of play with. This Taylor polynomial looks like it's being used with n equals to 2. And it looks as if the x naught point, remember in Taylor's theorem there's an x naught, some fixed point about which you're sort of centering the Taylor polynomial. It appears to be 0 from what we have right here. Okay, and then of course, as I mentioned earlier, the function looks to be the square root of 1 plus x. Okay, so what is p2 of x? This would be the Taylor polynomial of degree 2. I'll write down the formula for the Taylor polynomial of degree 2 again. Looks something like this. Okay, so there's my Taylor polynomial of degree 2. And means I'm going to need to take some derivatives here. So let me come back up here. And I'm going to just take, so let me just write this down again here. So we have, okay, so we have f of x equals the square root of 1 plus x. If I differentiate that once, okay, what I'll get is 1 over 2 radical 1 plus x. Okay, and if I differentiate it a second time, okay, just using the power rule and the chain rule, okay, if I differentiate this a second time, what will happen is I'll get a negative 1/4, and then 1 plus x to the 3/2. Okay, so that would be the form of what we're working with. Make that minus sign really obvious there. Okay. In all cases, I'm going to be plugging in 0 into those various expressions here. So when I plug in 0 for x, I'll get a 1 here. Here I'll get a 1/2, so this is plus 1/2 of x. And here I will get minus 1/4, and then there's a 2 factorial on the bottom and an x squared on the bottom. Okay? Well, this actually is the left-hand side. Okay, so this actually is the p2 of x is right here on the left side. Okay? Now remember that Taylor's theorem says that f of x is approximated by any Taylor polynomial I want, but then there is a remainder term here. Okay? So the remainder term, how does that work again? Well, the R2 of x, this would be 3 derivatives of f evaluated at c divided by 3 factorial times x minus x naught cubed. Right? Okay. So if I take a third derivative here, let's just do this really quickly. If I take a third derivative, we're going to get 3 over 8 and then 1 plus x to the 5/2. Okay, so this would be the third derivative of the function, and it's it's evaluated at c. C is some value between 0 and x in this case. Okay, but anyway, so when I plug that in, I'll get rid of my Taylor polynomial now. When I plug this into the remainder term, right, what we'll get here is 3 over 8 times 1 plus c to the 5/2 power. 3 factorial is 6, and then we have an x cubed on the right-hand side. The only thing you need to know about this is that it is positive. Because the fact that it's positive, it means that this remainder is positive, so that this whole expression then is greater than p2 of x. Okay? So f of x, which is this part, f of x, is greater than p2 of x because the remainder, which is right here, is positive. Remember, x is positive, c is between 0 and x, so it is positive. Everything here is positive. Okay, so that's the expression for the remainder. Okay, great. Then they ask us to use the second part of the question, part B here, asks us to estimate the square root of 1.3. Okay, estimate the square root of 1.3. Well, so of course, if I plug 0.3 in for x right here, then that's going to give us an estimate. So the square root, if I put in 0.3 for x, we see that the square root of 1.3 is greater than or equal to 1 plus 1/2 of 0.3 minus 1/8 of 0.3 squared, right? Okay. So this might be a little tough to just do in our heads here. Let's see. If I take 0.3 and I divide it by 2, I'll get 0.15. And here I'm subtracting, this is going to be 0.3 squared, which is 0.09. 0.09 divided by 8. Okay. So there's nothing, too magical about this. You can actually you could actually do this without a calculator, but it turns out to be 1.13875. Okay. So, of course, the square root of 1.3 is a little bit larger than that, but it's at least this much. And, of course, what we can do is we can try and figure out what the error would be in using that estimation. So we just used x equal to 0.3. The error is bounded by this, right? This is the sort of that gives you the maximum error. If I want to maximize this error term, which is, so I'm actually looking at part C of the question. Part C says, what is an upper bound for the error? Well, what is the biggest that this can be? Well, to get the biggest that this can be, I'm going to make the numerator as absolutely big as I can. So that would be putting in the biggest x that I can, which would be 0.3. Again, we're using the interval between 0 and 0.3. So the biggest x that you could plug in would be 0.3. On the bottom, I'll put in the smallest c that I possibly can, which would be 0. So actually c can't be 0, but you could sort of take the infimum value of c, if you will, for the interval in question, and that would be 0. So you would just end up with this expression here, and let's see, I came up with this, I calculated it to be 0.001685. So it's a very small error. The error turns out to not be quite that much, the exact error. But that's a good upper bound for what the error could be. So you can estimate the square root of 1.3 by this value, and you can know that it's not off by more than that, right? So the thing you have to be able to do here, guys, is recognize what the function is that you're working with. Recognize that there's a Taylor polynomial being considered, in this case of degree 2, right? And then be able to write down the Taylor polynomial of degree 2 and the formula for the remainder term, and then just do this little estimation with the remainder to come up with bounds on the error. Okay? So we've seen some nice examples with the mean value theorem, with Taylor's theorem, with derivatives, the applications of derivatives. We saw the chain rule come into play. Some of the other derivative rules also came into play. So there's some nice problems here. The solutions are all posted if you want to read how they look in very polished print. And you can always, of course, watch this again or ask me about it if you have any questions. Okay, I'm going to leave it at that for now, and hope this was useful, and we'll see you again real soon. Thanks.